Alright, so we've been talking a lot about functions, and continuing on that, another property of functions that we are interested about is the concavity of a function. So, what is concavity? Um, so basically, I'm gonna define that. So a graph of function f is concave up on some interval if f double prime is greater than 0 on that interval. Similarly, this graph is concave down on some interval if f double prime is less than 0 on that interval. So we see that the concavity of a function depends on the second derivative of the function, and essentially if the second derivative of the function is positive, then we call the function to be concave up, and if the second derivative is negative, then we're saying that on that interval the function is concave down. And what exactly does this concavity thing mean? So let me just give an easy example. So let's say we have a function f of x is equal to x cubed. We know that f prime of x is equal to 3x squared, and then f double prime of x is equal to 6x, right? And so we know that if we were to see the sign of f double prime, on values greater than 0, f double prime is positive, and on values less than 0, f double prime is negative. So we're saying that on x greater than 0, our function is concave up, and I'll just represent it like this, and then on values less than 0, our function is concave down. And when we actually graph out, y is equal to x cubed, if I can draw a straight line. If we graph out y is equal to x cubed, we get something like this. And this is a really poor drawing, but the idea is we established before that on its entire domain for y equals x cubed, the function is increasing on its entire domain, and that's not very hard to see. But when we're analyzing the concavity of the function, we see that on the positive end, so this quadrant, the concavity is positive, and then on this end, the concavity is negative. And what does concavity mean? When f double prime is greater than 0, that means f prime is increasing, right? So let me restate that. If f double prime is greater than 0, then f prime is increasing. And vice versa, if f double prime is less than 0, then f prime is decreasing. So in cases like, we can have f double prime be positive in both of these cases, right? And if f prime is positive, we know f is an increasing function. But if f prime is increasing, that's saying that f is increasing at an increasing rate. So in like more concrete terms, it just means that the slope of f as x continues to increase is continuing to be larger and larger. And we see that as this curve is getting steeper and steeper, right? And that's essentially what that's essentially what it means for a function to be concave up. It means that as we continue onto our domain, as x gets larger in that interval, concave up functions mean that we're increasing at an increasing rate, so our function slope continues to increase. Whereas if our function is concave down, that means our slope is continuing to decrease in that interval. And we see that as x being closer to negative infinity, the slope is like a very big positive number, and as it's getting closer to 0, we're reaching a slope of 0. And so that's essentially what concavity captures. It's capturing how f prime is changing, and so it's capturing how our slope of the function is changing. So we're really going like one layer deeper and really seeing how the slope of the function is actually changing as our x value is changing. And if f double prime is positive, it just means that our slope will continue to increase, and if f double prime is negative, it means our slope is going to decrease, and that has real repercussions on how the shape of the function looks. And that brings us to a concavity, like a definition of a concavity test, just to see what the concavity of a function is. And so let me state what the concavity test is. So a function f so function f's graph is concave up on any interval where f double prime is greater than 0, and it is concave down on any interval where f double prime is less than 0. And so it's just saying that we just find the sign of the second derivative of the function, and that tells us about the concavity of the function. And so let's do an example. Let's determine the concavity of the function y is equal to 3 plus sine x. So y prime is simply cosine x, and then y double prime is equal to minus sine x. And so we know sine's periodic, so let's just look at the interval of 0 to 2 pi, right? And we know sine is 0 at 0, it's 0 at pi. And those are the only points that we're worried about. And now let's look at what the sign of f double prime looks in between those intervals, right? So between 0 and pi, sine or negative sine x is negative, and then similarly between pi and 2 pi, negative sine x is positive, right? So we're saying that on any interval of 0 to pi, and then like on any multiple of interval between 0 to pi plus like 2 pi k, I guess, for like any real value or any integer k, we are concave down. And likewise, for any in the interval of pi to 2 pi plus 2 pi k, where again k is an integer, we are concave up. And that's all we need to do. We just utilize the concavity test to determine the concavity of this function. And that's just all it is. It's pretty simple. And so finally, after concavity, we have this other point that of interest, and it's called the point of inflection. And essentially, a point of inflection is a point where the concavity of a function changes. So how do we go about finding out the point of inflections? And so we should probably look at where the second derivative of the function is 0, right? So if f double prime is equal to 0, that can tell us about the sign of f double prime to the right and left of that function. So let's say f double prime is equal to 0 at some point c. And if we look at point c at point C, the value of f double prime is 0, and if we compare the value of f double prime at points greater than C and less than C, and if the sign of f double prime is different between those points, so if it changes from plus to minus or from minus to plus, then we can say that point C is a point of inflection. In all other cases, as for example, if the sign of f double prime remains the same between like if it was positive on this on the left side and positive on the right side, then C is not a point of inflection. So to find out points of inflection, we first calculate where f double prime is equal to 0, and then we look at the intervals to the immediate right and left of those points and determine whether or not those are inflection points or not. And so that's all for concavity and points of inflection. Just a bunch of definitions. Really, there's not, besides calculating derivatives, there's not much extra tools that you really need to find out and classify what kind of concavity a function has and where the points of inflection are.